Okay, and we're going to be working on number 3 right here, because number 3 is the first of our actual calculation problems. Number 1 and 2 on homework 2.4 are just conceptual, and we can talk about those in class. But number 3 is well, we have a jetliner coming in for a landing, and it says it's landing with a speed of 81.9 meters per second. So that's going to be our initial velocity, equals 81.9 meters per second. And well, what does a jet do when it comes in for landing? Well, it comes in at a certain speed, and then it comes to a stop. In fact, it says later on it comes to rest. So that's going to be our VF, or our final velocity. And the stop is 0. Oh, I already wrote 0. Is 0 meters per second. I'll just erase that there. 0 meters per second. And what else are we told? Well, we're told it comes to rest in 949 meters. Well, meters is a measure of distance, and so that's going to be the displacement, or the amount of distance that was taken up as this jetliner was landing. So that's 949 meters. And we're being asked right here, what is the acceleration? Constant. This jetliner is slowing down at a constant rate. And what is the acceleration? Well, we can probably figure out that the acceleration is going to be negative. That is, it's going to be working in the opposite direction that the jetliner is moving. But for right now, we just want to calculate the magnitude. So do any of our original equations for acceleration and velocity work? We know that acceleration is change in velocity over change in time. Well, we don't know the time, so we can't solve for acceleration. And we know that velocity, or we knew from before that velocity is our change in displacement over change in time. Well, that doesn't help us in terms of acceleration. So what we need to do is we need to use one of our new derived equations to solve for acceleration. And since we have our initial velocity, our final velocity, and we have our displacement, the equation that's going to be best to use is equation number 5, and that is velocity final squared equals initial velocity squared plus 2a delta x, or change in displacement. And so since we're solving for a right here, acceleration, let's move these things around. Let's subtract vi squared from both sides, minus vi squared. So it's going to be vf squared minus vi squared equals 2 times a times delta x. Now we can divide both sides by 2 delta x, which leaves us with vf squared minus vi squared squared over 2 times delta x equals our a acceleration. So let's move back up to the top here. So our acceleration is going to be vf squared. What's our final velocity? Well, it's 0 meters per second, that whole quantity squared, and that's going to be easy to calculate, minus our initial velocity squared, that's 81.9 meters per second. Don't forget that little point in there. The quantity squared, all that over 2 times delta x, and delta x is 949 meters. So our acceleration, if we calculate that out and punch it through, our acceleration is going to become negative 3.5 meters per second squared. Now the question asks us, what is the magnitude and the direction of its acceleration? And this could be stated in 2 ways. We were told initially that the plane was coming in from the south, so over here we could put, well, the initial velocity was 81.9 meters per second south. So our answer could be stated that the acceleration is negative 3.5 meters per second squared south, in a bracket right there. Or we could say that the acceleration is 3.5 meters per second squared north. That is, it's oriented in the opposite direction. So either one of these would be the correct answer. You just need to make sure you have the symbol indicating direction, or the actual direction, north or south, indicating direction. So the magnitude is 3.5. The direction can be indicated either by north or south, or by having a negative or a positive in front of it. 3.5 meters per second squared north, or negative 3.5 meters per second squared south.